Hello and welcome to Honors Function. In this lecture and the next one, we will be looking at an important topic in mathematics, infinite sums. An infinite sum is called a series. Let's begin. To add an infinite number of terms together, I need to have an infinite number of terms. Therefore, it is logical to fetch this infinite number of terms in a sequence, okay? And so given a sequence, A1, A2, A3, etc., 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 we can look at the infinite sum A1 plus A2 plus A3 plus AN plus forever. Now, what does it mean to add an infinite number of terms? How can this sum have a meaning? Well, to have a meaning, this sum must be finite, okay? If the sum is infinite, it doesn't have a meaning. That makes sense, right? If it is plus infinity, then the sum has no meaning. So to have a meaning, the sum must be finite. It must be a value, a number. If the sum is finite, there are many questions that follows now. Do the properties that we are very familiar with in the case of the finite sum apply to infinite sum? What are these properties? Well, you have the commutativity. A1 plus A2 equals A2 plus A1. You have the associativity. A1 plus A2 plus A3 is equal to A1 plus A2 plus A3. You have the distributivity. K times A1 plus A2 equals K times A1 plus K times A2. You are very familiar with these properties. Do these properties apply in the case of an infinite sum? I'm not sure. For example, if A1 plus A2 plus A3 plus forever is equal to a number, let's call this number L, then do we have that, for example, A5 plus A10 plus A1 plus A2, and then I will have all of them here except A5 and A10. Is this still equal to L? Not sure about this one, right? Likewise, does K times A1 plus A2 plus forever is equal to KL? Is this true? Well, we will not be answering this question in this course. For that, you would have to wait past a calculus course to start looking at the property of infinite sum. In this course, we're only going to be looking at a very specific type of infinite sum. They are called geometric series. It's the first one anyone studies when one studies series, and it's the easiest case. It's also a pretty important case, okay, to study any types of series. What is a geometric series? Well, as I've mentioned before, if you want to add an infinite number of terms, you need to have a sequence, right? You need to have a sequence of terms, ai from 1 to infinity. And now you can add all the terms together. By definition, a geometric series is an infinite sum of terms in a geometric sequence, okay? So a geometric sequence, you know what it means. When you go from one term to the next, you multiply by the same constant. So for example, a geometric series will be A1 plus R times A1 plus R squared times A1 plus R cubed times A1 plus Rn times A1, right? Because this is A2, this is A3, A4, and this would be An plus 1. And then, of course, it goes on forever. In this course, we are only going to be looking at this type of series. And this will be the subject of the next lecture. For now, let's try to understand what an infinite sum is. To understand infinite sum, I'm going to be looking at 3 concrete examples of infinite sum. The first one, when I add 1 with itself an infinite number of times, The second one, when I do 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7, an infinite number of times. And the last one, when I add 1 plus 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th, an infinite number of times. Okay? So let's start with number 1. So if you add 1 together an infinite number of times, I'm not sure you're going to get a finite sum, right? Let's look at it. I'm going to be looking at what we call the partial sum of a series. So a series is an infinite sum. Partial sum is a finite sum. For example, S1 would just be 1. S2 would be 1 plus 1. So S2 equals 2. S3 would be 1 plus 1 plus 1. And that's 3, right? S4, well, that would be 4. And Sn, well, that would be 1 plus 1 plus 1 n times. And that would be n. And so you see, these partial sums are getting larger and larger and larger. And therefore, if you add an infinite number of 1, it's not going to get anywhere. This would be infinity. And we say that the series diverges, okay? It diverges. It doesn't have a finite sum. It diverges. Basically, it has no meaning, okay? Before I move on to 2, let's try to understand why this series diverges. So let me look at this one now. 1/2 plus 1/2 plus 1/2 plus 1/2 forever. Now, every term in this series is smaller than the term in the previous series, right? 1/2 is smaller than 1. But I keep on adding 1/2 all the time. So, for example, what is S1? That's 1/2. What is S2? Well, it's 1. What is S3? It's 1.5. S4 would be 2. And on and on and on. They're still getting bigger, right? 1, 1.5, 2, 2.5, 3, 3.5. They're getting bigger a little bit slower than the previous one, but they're still getting bigger, right? And that would be true if instead of 1/2 you were taking 1 over 1,000, right? 1 over 1,000 plus 1 over 1,000 plus 1 over 1,000, an infinite number of time. So here it would be pretty small. S1 would be 1 over 1,000. S2 would be 1 over 500. So it's a very small number. But if you keep on going like that, Sn would be n over 1,000, right? And this would get larger and larger with n, right? If you take n equals to 10 billion, well, that's a pretty large number. 10 billion divided by 1,000 is a fairly large number. And if you take n equals to a quadrillion, not sure that exists, well, that would be even larger. So as n increase, even though the terms are very small, as n increase, the partial sum would increase, and therefore the infinite sum would have no meaning. So the first one we said diverges. Well, the second one is also going to diverge, and the third one will also diverge. What's going on here? What is precluding these series to have a finite sum? What you're adding is constant. It's the same quantity. And it doesn't matter if the quantity is very small. You're still adding a grain of dust that has the same size all the time. And these grain of dust put together will get larger and larger and larger. And they're going to create a mountain. And then they're going to create a galaxy. And then they're going to create a universe. It goes to infinity. All of them are moving towards infinity, right? Therefore, what you really want for a series to diverge, you don't want to add something that has the same size all the time. The size of what you're adding has to be smaller and smaller and smaller, okay? So for an infinite sum to have a finite sum, okay, if you want this to have a finite sum, then what you're adding together has to be smaller and smaller and smaller. What I'm saying right here is that this condition, the limit of an as n approaches infinity, must be 0. It must be 0 if the sum is to have a finite sum. Now, it's not because a sum is 0 that it will have a finite sum, okay? I'm not saying that if this is true, then you have an infinite sum, okay? I'm saying that if this is not true, you won't have a finite sum. Let me try to write down what I'm saying and what I'm not saying here, okay? Here is what I'm saying here, okay? If the an do not get smaller and smaller and smaller, okay, if the limit of an as n approaches infinity is not 0, then you can say that the infinite sum is not convergent, okay? If it has a finite sum, we call that convergent. It will be divergent. It will not have a finite sum. What I'm also saying is that if the limit of an as n approaches infinity is equal to 0, if the an's are getting smaller and smaller and smaller, it doesn't mean the sum will be finite. There is just no conclusion, okay? Let's move on to the second series. Series number 2. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus etc, etc, etc. This is a very important series in math. It's called the harmonic series. Okay? Harmonic series. Alright, what's going on with this series? Well, first of all, the terms do get smaller and smaller and smaller, right? I mean, if this is the first term, and this is the second term, then the nth term would be 1 over n, and as n approaches infinity, as n gets larger, this goes towards 0. So we do have that criteria that we're looking for. The terms are getting smaller and smaller and smaller. Does this series converge? No, it doesn't. Let me show you now how it was proved in the 14th century. Now, this proof is not going to be very rigorous. I'm going to be doing something that I'm not sure I'm allowed to do at this point. Well, I can tell you I'm allowed to, but you don't know that yet, okay? I'm going to be grouping terms together. So here we go. I'm going to keep this one alone, and then I'm going to take 2 terms here. The next grouping will take 4 terms. The next one will take 8 terms. The next one will take, did you guess? 16 terms. 16 terms here, 8 terms here, 4 terms here, 2 and 1. Right here, this is just 1 term. Okay? So you guessed what's going on here. 1 is 2 to the 0, 2 is 2 to the 1, 2 to the 2, 2 to the 3rd power, 2 to the 4th power, and on and on and on. Why am I doing that? Well, check it out. 1/2 is above or equal to 1/2, right? Okay. 1/3 plus 1/4. 1/3 is greater than 1/4. So this is above 1/4 plus 1/4. So this is above 2 times 1/4, which is 1/2. All right. What about the next one right here, the sequence of 4 terms? We have 1/5 plus 1/6 plus 1/7 plus 1/8. Well, 1/5 is above 1/8. 1/6 is above 1/8. 1/7 is above 1/8. And 1/8 is above or equal, it's actually equal to 1/8. Therefore, this sum of 4 terms is above 4 times 1/8, 4 over 8, 1/2, right? If you check that for the sum of 8 terms right here, it will be above 1/2. So check it out. 1 is above 1/2. 1/2 is above or equal to 1/2. 1/3 plus 1/4 is above or equal to 1/2. This one right here is above or equal to 1/2. This one right here is above or equal to 1/2. Therefore, what you have right here, this sequence, and then the next one would be above or equal to 1/2, and if you take 16 terms right here, right? And then that would be true all the time. Therefore, the harmonic series 1 plus 1/2 plus 1/3 plus 1/4 plus etc. etc. would be above 1/2 plus 1/2 plus 1/2 plus 1/2 plus, and we know that this one does not have a finite sum. This one diverges. This one is equal to infinity, and this one is above it. So it's also equal to infinity. Therefore, the harmonic series diverges. Let's look at the last series now. Okay, so the third series does have the property that the terms are getting smaller and smaller, right? This one, on the other hand, has a finite sum. I'm going to show you this in two ways. First, a geometric way, and second, an algebraic way. Let's go over the geometric way. If you take a square of side 1, right here, here's a square of side 1. Okay, 1. All right. If you now divide this square in 2, what is this area right here, A1? Well, A1, if A1 is the area of this rectangle, it is 1/2, right? Oh, okay. So this is 1/2 right here. I'm going to divide the remaining rectangle in half right here. So I have 2 squared. So this is a square 1/2, right? From here to here. And this is also 1/2. So what is the area of A2? Well, A2 is 1/2 times 1/2. So it is 1/4, right? So A2 is 1/4 right here. I'm going to do the same with the remaining area. I'm going to divide that in 2. So here I have 1/2, and now 1/2 divided by 2, this length, this side is 1/4. So what is A3? Well, A3 is 1/2 times 1/4. So A3 is 1/8. All right, we got this rectangle right here. I'm going to do that one last time. I'm going to take this remaining area and divide in 2. So I'm going to call that A4. Okay, so this is 1/4 and this is 1/4. So A4 has an area of 1/16. Here we go. Here is A4. And now what are you going to do? You're going to repeat this. Here's would be A5, and that would be 1/32. And then you would have A6, and that would be 1/64. A7, 1/128. A8 is getting really smaller right here. 1/256, and on, and on, and on, right? So, I'm going to add all of these areas together now. I'm going to take all of these areas and I'm going to add them all together. So I have 1/2, that's A1, plus 1/4, that's A2, plus 1/8, that's A3, plus etc., etc. So basically I'm adding 1/2 to the nth. Forever, forever, and ever, and ever, and ever, and ever. What do you find when you add all of these areas? You find the area of the entire squared, right? This is the area of the entire squared. And this is 1. Haha! This is the first infinite sum that you are looking at that has a finite sum. And this is a beautiful geometric proof of it. Now we have to be careful. This is not exactly the series we started with, right? We have proved that this sum is equal to 1, but we have to add 1 to it. So 1 plus 1/2 plus 1/4 plus 1/8 plus etc., etc., etc. is equal to 2. Here we go. This is a geometric proof of it, and it's quite pretty. Let me show you now the algebraic proof of it. Here is a series we're looking at, and I'm going to assume, it's going to be a very big assumption, that it has a finite sum, that this series is finite. So L smaller than infinity. Okay? Now, I'm going to do something here that I'm not sure I can do, but hey, let's see where we're going with this. I'm going to multiply both sides of this equality by 2. So far, so good. I'm allowed to do that. What I'm not sure about is this right here. Am I really allowed to distribute over an infinite sum like that? Let's just do it and let's not wonder about it, okay? So let's do it. So what would you find if you were allowed to do that? You would find 2 plus 1, right? 2 times 1/4, 1/2. 2 times 1/8, 1/4. 2 times 1/16, 1/8, plus etc., etc., etc. And lo and behold, what is this? This is the sum you called L, right? This is L right here. That's L. So look at the equation you have. You have 2L equals 2 plus L. 2L equals 2 plus L. Therefore, L equals 2. If this sum is finite, it's equal to 2. All right? Before going over one example of an infinite sum, I want to make two remarks here. The first remark, for the harmonic series, I've grouped terms together. Am I really allowed to do that? Can we just group? This is using associativity and commutativity, basically, right? Well, I'm not sure. Check out this series right here. 1 minus 1 plus 1 minus 1 plus 1 minus 1, right? If you group terms like this, what are you getting? 1 minus 1 is 0 plus 0 plus 0 plus, well, if you add an infinite number of 0, you're going to find zeros, right? So that's all right. But now if you do this, 1 minus, and here I'm going to group the second and the third, so it's 1 minus 1, right? Because you have to distribute right here, and you would get you plus 1, right? All right, now let me group the fourth and the fifth, so minus 1 minus 1. Now let me group these two right here, minus 1 minus 1, right? And I'll do that forever. So what does that give you? That gives you 1 minus 0, minus 0, minus 0, minus 0. Well, if you subtract an infinite number of 0 from 1, you're gonna get 1. All right? So here's a seemingly contradiction here. Depending how you group terms, this can give you 0 or 1. That doesn't make sense, right? A sum cannot have two different values, right? So what's the problem here? The problem is that the terms of the series do not have a constant sign. They alternate their sign: positive, negative, positive, negative, positive, negative. In the three series we looked at, all the terms were positive, okay? That's a pretty big distinction. We cannot enter further in the details here. Here's a second remark now. We said the harmonic series is not finite, but if you now square every term of the series, right? If instead of adding 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus etc., 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 if you square every term of the series, this one would be finite. It's kind of interesting here. And of course, we can't prove this. Again, if you want to dig further in the topic of series, you'll have to wait a Calculus 2 course. Let's go over an example now. So, if you drop a tennis ball onto a horizontal floor, it will bounce back up part of the way. If left to its own device, it will continue to bounce, the height of the bounces decreasing each time. The ratio between the heights of consecutive bounces is constant. Well, that means you're dealing with a geometric sequence, right? Right? If the ratio between two consecutive bounces is constant, hn plus 1. Okay, so hn is the height. I mean, this is what I'm going over the question right here. hn is the height after the n plus 1 bounce. So hn plus 1 over h sub n is constant. Let me call that r. Well, that would mean that hn plus 1 is equal to hn times r, and that's a geometric sequence, right? Okay. And I'm also telling you that the same is true for the times between consecutive bounces, okay? So the times between two consecutive bounces form a geometric sequence. Question 1. The tennis ball is dropped from a height of 1 meter onto a concrete floor. After its first bounce, it rises to a height of 49 centimeter. So hey guys, be careful of the unit right here, meter, centimeter, right? Let's call the height after the nth bounce hn. Find the formula for hn. So this should be a pretty simple question. So here's the ball. This is, the first one is 1 meter. Bounce 1, okay, height 1. Bounce 2, height 2. Bounce 3, height 3, and on, and on, and on, right? So I'm gonna call this first height right here, I'm gonna call it h sub 0, h naught. The second one, we're gonna call it h1, right? After the first bounce, that's h1. The third one, okay, I'm gonna stop here because it's getting really squeezed, it's h2. All right, what do we know? We know that h naught is 1, and h1 is 0.49. Okay, careful, it has to be the same unit, right? Meters. And we know that the ratio is constant, so 0.49 over 1 is 0.49. So the third bounce will be 0.49 of h1, so 0.49 squared. The third one is 0.49 cubed, and on and on and on. Therefore, the nth bounce would be 0.49 to the n. Okay? Here is the formula for the nth bounce. What is the total distance the ball has traveled when it bounces nth time? Actually, here, there's no th, right? N times is better. When it bounces n times. Here we go. That's a sentence. All right, so if it bounces n times, what do you have? Well, let's see. So look. Here's the first bounce. Here's the second bounce. Here's the third one. Fourth, fifth, etc., etc., etc. And then n bounce right here. That's the nth one right here. Nth bounce. All right, so what's going on here? So let's call the total distance dn. Why not? Okay, dn, the total distance after the nth bounce. What is it equal to? Well, it's equal to h naught, right? The first one right here. And then it's equal to 2h1, right? h1 up and h1 down, plus 2h2, same thing, h2 up and h2 down, right? Plus, okay, and then 2hn, hn up and hn down, 2hn. So, of course, I'm going to write that as 1 plus 2, and here I'm going to factor the 2's, and I have h1 plus hn, and this is what we've been calling Sn, right? So it is 1 plus 2 times, okay, so first term, it's a geometric sum, so first term, 1 minus 0.49 to the n over 1 minus 0.49, right here. So if you simplify that, you would find that dn is equal to 1 plus h1 is 0.49 over 1 minus 0.41 is 0.51 times 1 minus 0.49 to the n, right here. That would be the formula. And so it is 1 plus 49 over 51 times 1 minus 0.49 to the nth. That's the distance it has covered after the nth bounce, right here. All right. Find the total distance the ball travels before it stops bouncing. What happened in the previous formula if n approaches infinity? So the total distance, if I call that d, it would be the limit of my dn as n approaches infinity, right? And so it is the limit of, so what's the n right here? Right there. 1 plus 49 over 51 times 1 minus 0.49 to the n as n approaches infinity. So let's look at that. That's going to be pretty simple. This has a base smaller than 1, so it goes towards 0. Therefore, 1 minus 0, that approaches 1, and therefore the whole sum approaches 1 plus 49 over 51. So that would be 100 over 51, and therefore, if you type that in your calculator, you would find D is about 1.96 meters. Okay? 1.96 meters. Okay, I'm gonna let you do question 4 and 5. Thank you for watching.